Hey guys, just wanted to go over metabolism, which is chapter 8. I got a lot of questions on it. So I just wanted to go over that. I also meant to make this really fancy and nice, but I didn't have time over the break like I thought I was going to. So you'll have to deal with it from scratch, and hopefully you can read it and it makes sense. And yeah. Um, okay, so let me flip. Okay, so I'm going to start with glycolysis, and then we'll just work our way through the citric acid cycle and the electron transport chain. So to start with, each of these dots on this line are representative of a carbon. So this first like six carbon molecule is called glucose, and we're just going to consume this in our diet. Because glucose is so small, it can go in and out of our cells most as it pleases. Which, if we're trying to break it down, is a problem if it just leaves halfway through. So in order to make it bigger, we are going to add a phosphate to it. I just want to point out that these numbers next to it is not how many ATPs I'm using, rather it's how many phosphates. So ATP has 3 phosphate and ADP, that's a P, not a D, has 2 phosphates. So ATP comes in, gives glucose a phosphate, which turns it into ADP. So the phosphate in the 6 carbons are now called glucose 6 phosphate. We're going to do that process again to add another phosphate to the other side. So ATP is going to donate a phosphate, become ADP, which adds that phosphate on the other side, which becomes fructose 1,6 biphosphate. At this point, we're just going to split that molecule down the middle. And so that is going to create DHAP, which has the phosphate in the front, and we have glyceraldehyde 3 phosphate, or G3P, which has the phosphate at the end. DHAP is basically useless in the body. So we are going to convert DHAP into G3P. I also want to correct myself. DHAP may have a purpose, but those processes are completely useless in the body right now. So G3P. So now we have 2 molecules of G3P. So these next steps that I'm going to go through, they happen twice. So you're going to have a phosphate, which is just going to be floating around in the cytoplasm, and the phosphate is going to come in and attach itself to that G3P. At the same time that it's getting attached, you have NAD+, which is going to come in, still hydrogen and 2 electrons, and become NADH. So that is how that process happens. So something's getting taken away and something's getting added at the same time, if I remember it. And at the end of that process, we have 1,3-bisphosphoglycerate, which is phosphate on both sides of the 3 carbon molecule. And now we're going to take those phosphates off. We take ADP, which again has 2 phosphates. We're going to come in still a phosphate, which will give us ATP. And since we had 2 phosphates, we're going to do that process twice, which will give us 2 ATPs and leave us with pyruvate. Again, we do those steps twice because we had 2 molecules of G3P. So at the end, we're going to end up with 2 NADHs, which we made here, 2 pyruvate, and we made 4 ATPs. So we did this 1, 2, 3, 4 ATPs. But at the top, if you remember, we used 2 ATPs. So we made 4, we used 2, which gives us a net of 2. And then the next cycle depends on whether we have oxygen. So if we don't have any oxygen, we're going to go anaerobic, and we're going to go from from NADH, we're going to give back that hydrogen and those 2 electrons and become NAD+. When we give pyruvate, that hydrogen and those electrons, he becomes a lactate, or lactic acid. So that's if we don't have oxygen. If we do have oxygen, we are going to go to the citric acid cycle. So glycolysis happened in the cytoplasm. The citric acid cycle is going to happen in the matrix of mitochondria. So if we have oxygen, we're going to take that 3 carbon molecule called pyruvate, and we're going to move it right into the mitochondrial matrix. Once it's in the mitochondrial matrix, it's going to release the carbon dioxide, and NAD+ is going to come in, still hydrogen and 2 electrons, and become NADH. So that's all going to happen, which is going to leave us with a 2 carbon molecule. This 2 carbon molecule, you can call it acetate or acetyl, and then an enzyme called coenzyme A is going to come in and attach itself, and so together they become acetyl-CoA. At this point, we have something floating around called oxaloacetate, which is a 4-carbon molecule, and it's going to come in. So oxaloacetate and acetyl-CoA bind together to create a 6-carbon molecule called citrate. So citrate starts the citric acid cycle. So citrate is going to lose a carbon dioxide, and NAD plus is going to become NADH, which will leave you with a 5-carbon molecule. And you're going to repeat those steps again. CO2, and then NAD plus, NADH, which will give you a 4-carbon molecule. At this point, you have made ATP. So an ATP comes out, and FAD is going to come in, so 2 hydrogens and 2 electrons, and become FADH. And then you're going to have NAD plus come in, so a hydrogen and 2 electrons, and become NADH. And the end product of that is the oxaloacetate, which then again will combine with another acetyl-CoA. One thing that's important to know about this point is, remember, we had 2 pyruvates from the glycolysis. So this cycle happens twice. So at the end of this cycle, we have NADH. We made 6 in the citric acid cycle. Wow, I can't type. But we also made 2. Oops, can't type. We made 2 in that pyruvate oxidation, or that first part at the beginning right here. We made 2 right there. So maybe I should, I don't know how to spell it. This is only going on the internet. No big deal. Okay, so that's your NADHs. The next thing we have is our ATPs. In this cycle, for each time we went around, we made 1. So ATP 1 time, and we went twice. We made 2 ATPs, and then our FADHs, we made 2, 1 for each time we went around. So that is the citric acid cycle. The next thing is the electron transport chain. So with the electron transport chain, we're going to take all the NADHs and all the FADHs that you made, and you're going to kind of tally them together. So from glycolysis and from citric acid cycle, we made 10 NADHs and we made 2 FADHs. We just kind of keep track of those. So what's going to happen is NAD plus is going to come to this protein complex 1. So we have protein complex 1, 2, 3, 4, and then ATP synthase is the green one. So with NADH comes to protein complex 1. And NADH is going to drop off his 2 electrons, and he's going to become NAD plus. At the same time he's dropping off those 2 electrons, 4 hydrogens get pumped across from the matrix of the mitochondria to the intramembranous space. We had 4 come through. And this part I like to think of it as a softball game, or just a game of catch. So those 2 electrons are going to be the ball. So we're going to throw those 2 electrons from protein complex 1, and we're going to throw them to protein complex 3. At protein complex 3, we're also going to pump 4 hydrogens across. And then we are going to do that again. So we're going to throw the 2 electrons from 3 to 4, and at 4 you also pump 2 hydrogens across. And then lastly, you're going to throw those electrons to oxygen, which is already in the matrix, and those electrons are going to attract 2 hydrogens to the oxygen, which makes water. So water is going to be a byproduct of this process. So in total, we pumped across 4, 8, 10 hydrogens for every 1 NADH. But we had 10 NADHs. So in total, 100 hydrogens got pushed through for all our NADHs. FADH is going to do something similar, except for he's going to start at protein complex 2. Protein complex 2 is a peripheral protein, meaning it doesn't go all the way through the membrane, so it doesn't have the capability of pumping hydrogen through. So no hydrogens go through it too. So FADH will come, drop his electrons off at complex 2 and become FAD. We then are going to throw those electrons. So 2 electrons go to protein complex 3, which will pump 4 hydrogens across, We then throw those electrons to complex 4, which will have 2 hydrogens across. And lastly, we throw it to oxygen to make water. So in total, from F88, we pumped 4, 6. So 6 hydrogens came across, and we had 2 F88s. So 6 times 2 is 12. So 12 hydrogens came across for all the F88s that we had. And so in total, 112 hydrogens came across. So that's important to take care of your math there. The next thing to understand is you have a high concentration of hydrogen in this intramembranous space, and you have a low concentration in that matrix of mitochondria. So your hydrogens are going to want to go from high to low concentration. And so ATP synthase is a channel that those hydrogens can go through to follow that concentration gradient. So every 3 hydrogens, approximately 3 hydrogens that go through ATP synthase, 1 ATP is made. And so you get approximately 34-ish from this. And the way I did that math, you can kind of see it up here in my little chicken scratch. So we got 10 hydrogens through for every 1 NADH. And for every 3 hydrogens, we make 1 ATP. So if we take 10 divided by 3, we make about 3 ATP per NADH. And we had 10 NADHs, so 3 times 10 is going to give us 30. And then, again, we got 6 hydrogens through with our FADHs. It takes about 3 to make 1 ATP. So 6 divided by 3 is 2. And then we had 2 FADHs, so 2 times 2 is 4, giving us about 34 ATP for the electron transport chain. If we take all of these processes together, so if we take glycolysis, the citric acid cycle, and electron transport chain, we're going to make about 38 ATPs because we had 34 from the electron transport, 2 from the glycolysis, and then 2 from the citric acid cycle. So for a total of 38. Again, it's really important to keep track of how many things you're making per step, just so at the end you can add them up and keep them together. But this is a little video that goes over chapter 8. I hope it helps you review and study the things that you need to know. And then also, if you go to 8.1 in the assignments and then the required media, there are practice questions there. I highly recommend doing them to test your knowledge. I also recommend people writing out this process step by step through glycolysis, citric acid, and the electron transport chain. As I've been tutoring people, one thing I've noticed is they say they know it, and then as they go to write it, they don't know it as well as they thought they did. So the more you write it, the better. Don't just know it conceptually, you have to be able to write it and explain it to somebody. But I hope this helps, and have a great study session, and good luck on your test.